So I plan to talk in great detail about ODP 11 and 12. But if there's any other questions first or after, we can talk about those too. So if there's something you want to talk about other than ODP 11 or 12, we can do that now. Okay, let's talk about the midterm.
It's Monday, right?
It is Monday. As you were kind of point out in here, we don't have class Friday.
It's a good thing, because otherwise the choice was today or Monday.
I'd be like, where is everybody? They didn't show up for their midterm. So midterm will be 15 minutes, closed book, 2 double-sided pages of notes. Or single-sided, your choice. I will warn you that writing down code in your notes probably will not help with some of these questions. If you don't remember the syntax for a structure statement or something, yeah, go ahead and put that in your notes. But try to put into your notes things like algorithms, okay, or the ideas that are kind of flippy in your head and you're not quite sure if it's this or that, right? Things like that that will help you jog your memory and so on. So you can expect some programming questions, probably not complete programs start to end, probably no 1,000-line programs, probably more things like write a few lines of C code to perform this change on this linked list, or to create a structure that has these fields and then do something with these fields or pass it to a function or something like that. Most of what I ask you to write a program for will probably be a few lines of code if you do it in a sort of succinct way. And I can tell you up front that if you're welcome to bring copies of your code with you if you want to, squeeze it down and fit it on 2 pages. But looking through code to find answers to questions probably will not work, because I'm not going to ask you to do things that you've already done in your programming assignments, probably. Okay? So you're going to have to go back to the understanding of what does this node point to in a linked list? Or how do I access the thing that this is pointing to and make it point somewhere else? Stuff like that. Okay? So work with your programs, work with your code, go back and review it, rewrite it, talk it over with other people. Those kinds of things are good ways to prepare for the programming parts. Other parts, so I'll probably have some short answer or multiple choice or matching, particularly for things that we haven't done a lot of programming, like stacks and queues. We didn't really code those. We talked about some code, but I'm probably not going to say code up a working stack package. Okay? But you should know what stacks do. They're last in, first out. There's a stack pointer. They can overflow if there's too much. They can underflow if it's empty and you try to pop. Queues have a pair of ends. There's a head and a tail, and you insert the tail and extract from the head. And we usually implement them with a circular array and so on and so forth. You should think about the structures we talked about in terms of abstract data types. There's 2 aspects to most of these structures. There's the ADT view of a hash, for example, right? It's a collection of objects. We can store things and associate them with a key. We can fetch things based with a key, and we can initialize them. We can delete things based on a key, and so on. And then there's the implementation details, which are your coding. And those are sort of 2 separate things, right? The ADT is sort of the user's interface to the structure. The implementation is what goes on under the hood. Okay, the abstract data type definition of a car is it's a vehicle with a pedal for moving and a pedal for stopping and a wheel for steering. Okay, that's a simplified abstract car type. But what does it do when you push the pedal? Does it move a rod that opens a flap to let gasoline flow? Does it change a resistor that changes an input to a computer that causes a valve to open? that's the implementation of the abstract notion of a gas pedal.
Your definition of the type didn't require wheels.
Yeah, well, it moves, so it could be a flying car. But it's got a way to go and a way to stop and a way to steer. So it includes skateboards too, I guess. All right, what else do you want to know about? I have a list, but I'm not going to display it to you. I haven't written it yet, but I got a pretty good idea.
For the one-day pros, do you know like the test file and the grade file different?
Yes.
Oh, okay.
Yeah.
That's the first time I've had that problem. I got the assessed 10 and the grade's only 6. I'm just like trying to figure out what the hell's going wrong.
Yeah, generally I try to have the test file test the same kinds of things that the grade file tests. But sometimes something will pass one and not the other. Sometimes you might get a 6 on the test and you might actually get a 10 on the grade. So it's always worth taking that shot, you know. So hash tables. I probably won't have you code anything for a hash because that's what you're working on this week and next week. But I will ask you questions about hash tables, about how you store things, how you fetch things. I may ask you to implement a hash function to take a string and convert it into a number or something like that. Or I may give you a picture of an empty hash table and say, okay, if I store this key using this hash function, where would the key get stored? And now if I store this key, where would that get stored? And you might need to deal with collisions and so on and so forth. So I might give you something where you fill in the results of running an algorithm. And probably some conceptual stuff on pointers and things pointed to and structures. Maybe that segfault, no segfault question I joked about will actually show up. I don't know. The stuff you've been doing, right, is all basically fair game, but it's stuff you've been doing, and I'll try to hit the stuff that has been more relevant as opposed to some obscure thing that might have been mentioned once 3 weeks ago. So hopefully it'll be the major themes. All right, and it'll be 50 minutes, so try to come on time. But I'll probably start at like 10 minutes after class starts. So we can spend 10 minutes on questions or whatever, and if people come in a little late, that's okay. And then we'll do a 15-minute test, we'll take a break, and then some sort of lecture.
That's Wednesday?
Monday.
Monday, okay.
Today's Wednesday.
Right.
Yeah. I should give you 2 hours since you're like the few and the brave who showed up for the second section. Like the whole time. Then I get in trouble. All right, other questions? Yes.
I actually wondering about the store function on P3.
Okay.
So it says to search for the key and see if it's already found in the table and return -1 and then hash the if it's not found, hash the key afterwards.
Mm-hmm.
But shouldn't you be hashing the key beforehand and then searching for it?
Yeah. Except that the easier way to do this is just call your search routine. So inside store, you're not actually going to run the hash function explicitly first. You're just going to say search for this key and see what it returns.
Okay.
But if you want to actually code the search inside the store, then yes, you definitely need to hash it first.
Okay.
So, but I think when I wrote it, I was being lazy.
It makes sense because your fetch has to hash in order to fetch.
Mm-hmm. So the hash will definitely get run first. But it might not actually say hash inside your store code.
I took that to just mean I should write fetch first.
Yeah. And you can do the same thing in delete. I think delete I might have actually said search first. Nope, I didn't. Actually, want, you can search for it first, right? You don't have to do these algorithms with these 4 steps, but it has to, whatever you write has to end up doing the same thing that these 4 steps do in the end. Okay, so when I give you pseudocode, you're not bound to following that pseudocode line for line. You can do whatever it is you like to do, but that's a description of what the function should accomplish. Other questions, comments? All right, let's look at the ODPs. So, a couple of general comments on ODPs. I think I might have said this on Monday, why they're called one-day programs. Right, it's not that they're so easy that they can be done every day, it's that it's really important to do it before the next day begins. Right, so that you can build on it. So ODP 11 was done in that spirit. ODP 11 took some people quite a few hours to do. Okay, and if I had never done something like ODP 11, well, I did in the past, right, and it took me quite a few hours the first time I tried to write something like that. It's not a simple program if, while you're writing this program, you're learning how to think about structures and pointers and dynamic memory allocation. Okay, it's a fairly hairy beast to grapple with. But it's something that needs to be grappled with, and you need to wire your brains in order to grasp these concepts and put them in a way that you can work with them in your heads. And you want that to happen at the beginning of the 2 weeks for PA3, not 3 days before, right? Because if 3 days before is the first time that you're trying to write that init function, or init test, and it's taking you 3 or 4 or 5 hours to do that, and at the end of that, you're exhausted, you're behind on physics, and you've got the first of several functions you need to write, that's pretty daunting. Right? And chances are you're either going to be in a mad crunch for the next 48 hours or you're just not going to finish PA3, and then the whole exercise will repeat on PA4 and so on. The time that you spend doing ODP 11 and ODP 12 and probably 1 or 2 more of these ODPs will return wonderful dividends, right? Because you're moving to a point where you're getting these internal concepts of pointers, dereferencing pointers, what it means to malloc, right? Things like that. And we're almost at the point where it's going to start getting easier, right? For some people it already is. But if this has been a really steep learning curve, right, it's like going uphill on a bike. The other side is wonderful, right? Because you're going to come off the top of this with all these extra mechanisms in your toolbox. And once you can start thinking in terms of, you know, here's a block of memory and it points to that and that's pointing to this other thing, then this stuff becomes really easy, right? And this is the real challenge of 222, is the stuff that we're doing in ODP 11 and ODP 12. And once those are internalized, and if they don't feel like they're getting there, they will in the next few assignments and throughout PA3. Once you're at that point, it gets easier and smoother because it's just kind of the same thing over and over again. We can talk about 50 different kinds of data structures, but implementing them is still going to involve, right, defining a struct, figuring out what the fields are, which ones are pointers, which ones are actual data, allocating space so they can point to something and setting up the fields of that thing and so on and so forth. And it's just the same thing over and over again. And then we get into Java and we never say the word pointer again because there are no pointers in Java. But we use the same concepts, right? And everything that we've done in working with pointers prepares us to be able to smoothly transition over to an object-oriented language like Java or whatever else we choose to use, C#, C++, etc. So it's in some point the hardest part of the course, but it's going to be the most rewarding. Okay, so hang in there with that.
So you're going to do a couple more one-day programs?
Oh, no, but they'll go back to more like what the first one or two might have been like, which is like just, you know, do this and it's done. And maybe there's something you have to figure out, but it might take you 10 minutes instead of 10 hours. Right? Not cheap, but yeah. But I'll try to make some interesting. All right. Did I do a once over on size of on Monday? Did we go through my code sample that looked at 3 different uses of size of? I'll show you my code, tell me if we went through this.
You wrote it up on the board,
We talked about it a little bit when I got it wrong and did a pointer on accent,
but I have a feeling it's something that can be reviewed too.
Well, okay, let me do this, and if it's totally redundant, just throw something my way. So size of, and I'm going to suggest that you use size of with an argument that is a type of data. Okay, where type could be integer, char, double, integer pointer, char star star, or something more complex. I'm switching to blue. Something more complex like struct, my stuff, struct, stuff star, or something like that. A type of variable. Yes?
Something I got confused on, that kind of brings me to it. Hash, is that a data type, or is that a, you know, where you define it and make it a data type?
So
Or is it
hash,
either of those?
so there's a type def. So type def, and it was struct hash entry
Star.
star. That's what I call a hash. So when you say hash, it's exactly the same thing as saying struct hash entry star.
Okay.
Okay, it's just a synonym. Type defs don't do anything except say, when I say this, I mean this. And it's just easier to say hash than to say struct hash entry star. But it's just a symbol
When
replacement.
you understand what hash means, yes.
Okay,
But
yeah.
when you don't, then it's very
Right,
easy.
right. So we could define type def char star string. And every time we say char star x, char star x, char star x, now we can just say string x. And it means char star x. All right. So what I like to see in size of is a type of a variable. It could be hash or string or struct hash entry star or char star or any of these other things. You're allowed to put in the names of variables, but it can get you into trouble. It's more susceptible to misunderstanding. So I suggest when you use size of, you use it for one purpose only, which is I need to know how much memory a certain type of variable requires. So for example, if you want an array of 100 integers, well, if I know that ahead of time, I can just say integer x 100. But if I don't know that ahead of time, I'm running a program and I want the user to type in a number, and then I want to make an array that holds that many integers. I can't say int x bracket whatever the user types in when the program runs. So what we do is we say integer star x. And that means x will be an array. And the user types in a number, so we'll go pseudocode, print how big. And I'm going to input some number I. It's basically, we can just say input I. We got to f gets a buffer, we got to scanf and store the result in address I, and so on. But at some point in our code, I tells us how many integers we want from this array. Okay, so if they typed in 500, I is equal to 500. We want to make x an array of 500 integers. So the way to do that is to call malloc. Call malloc and ask it to give us enough space to store 500 integers. And then we're simply going to say X has the address of the beginning of that block of memory. So what number do we put in here for malloc to say give us enough space for 500 integers?
500 times size of
We can do 500 times the amount of space we need for one integer. 500 times size of int. And if you do it like this, I think you're less likely to do something different from what you hoped.
At one point, I wound up having kind of a goofy error when I was trying to return a pointer to something, and the variable was already a pointer. It was I think it was a hash star or something like that.
Mm-hmm.
But I wound up at some point just in my code putting an ampersand in there because I was trying to get the address of it.
Mm-hmm.
And so I wound up having the address of a pointer, and it was this. It still registered as a pointer, but it was like a longer pointer.
Yeah.
Like, I'm trying to figure out what happens technically if you put address of a pointer.
It should be the same as a pointer.
That's what I thought, but it goofed it up. It was really
It'd
weird.
be interesting to see the example.
I'll try and unbreak
Because
it.
not all pointers are the same. Sometimes they come from a different section of memory and maybe it's doing something, but I wouldn't think so.
Interesting.
Yeah, see if you can find an example again. All right, so if I want an array of 500 integers, I can do this. If I want an array of 500 struct hash entries, I can do this. Right, and a hash entry is this complex data type that has a key, a value, and in use and a deleted. And I don't know how many bytes that takes, but the compiler knows. The number of bytes it takes is size of struct hash entry. So if I want an array of 500 of those, 500 times the size I need for one gives me enough space. Now, if I do this, 500 times size of struct hash entry star, bless you, that's giving me enough space for 500 pointers to hash entries. A pointer to a hash entry probably needs 8 bytes. This thing needs 24 bytes. And if I had 10 integers, it would need 50 or 60 bytes. But no matter how big that structure is, a pointer to it is always going to be 8 bytes on our server. So if I really want an array of pointers, this is the way I do it. But if I want an array of hash entries, don't get the size of a pointer to a hash entry, just use a hash entry. Find how big that is. Not just lose my internet. Good. Did not just lose my internet. All right, so some sample code. I have a structure called big. It's got some stuff, some more stuff, some string, another string, and some array. Big is a big structure. Right? Just this array of 100 integers is going to need 100 times 4, 400 bytes just for that array. And then another 16 for the pointers, and then another 8 for these 2 integers. So this is probably going to need 424 bytes for one variable of type struct big. So if I want to know exactly how many bytes it needs, I can say size of struct big. And I've got a print statement here which says print size of struct big equals, and I just print out size of struct big. Now if you try size of struct big star, I just finished saying that's not going to give you the same number. That's going to tell me how big is a pointer to this structure. And the reason we use pointers is because it doesn't matter what they're pointing to, they're always the same size. one reason to use pointers. So this will print out what the size of a struct big star is. And then here's something that I saw in one piece of code, size of 100 times size of struct big, to see how much space we need for 100 struct bigs. And that might look reasonable, but it's not, because size of expects a type of variable and it tells you how much space do you need for that. Well, what I have here is size of struct big, that's 424, times 1,000, that's 42,400. Size of 42,400 says how many bytes do I need to store the number 42,400? And it's actually going to be 8 bytes. But it's not going to be the size of 100 struct bigs. So you got to kind of do the calculations yourself. So there's the actual numbers. All right, so that's the first thing with these programs is be careful how you use size of. And if you're not sure what size of is going to give you, write some code like this, right? And play around with it and make sure it's doing what you think it's doing. And if you use size of to get the size that you need for 101 of your hash entries and it comes back with the number 8, you know that you're using something wrong. Right, so go back and look at the code and try to get some number that's at least in the hundreds, right? All right, so let's draw pictures. And again, if I did this Monday, stop me, but I don't think I did. All right, so here's the hash structure we're working with. This file is available under /temp. I posted an announcement about that. So you can type it in or copy it from the original place or just copy it from /temp. But if you're going to use this as an include file, put it in your current directory and then include it with quotation marks, not angle brackets. Okay, quotes say look in my current directory. So let's look at what this hash table actually looks like. So our hash is, find down below. Our hash is a struct hash entry star. So when we say hash with an uppercase H, it's pointing to a struct hash entry, but it's actually being used as an array of struct hash entries. So this is an array consisting of, be more generous, (101) struct hash entries. This is index 0, index 1, index 2, index 100. And each of these is a struct hash entry. So what is a struct hash entry? It has 4 fields. It has a key, it has a value, it has an in use, and it has a deleted. In use and deleted are just integers. So they're actually sitting in these memory locations. This is a memory map redrawn. This is the location that hash points to. So it's the beginning of our array. We have some collection of bytes for a key, followed by bytes for a value, followed by an integer and an integer, followed immediately in memory by another key, value, integer, integer, and so on 101 times. key itself is typedef as a car star. So this is not a string. It's not a collection of letters. We can think of it as a string. But if our first key is hello, we don't find the letter H in here. Okay, this is important. What we find here is a pointer to somewhere in memory where we have our actual key, followed by a null terminator. And this entry down here, table bracket 1 dot key, is not a set of letters, it's another pointer to whatever the next key is, and so on. All right, value is also a pointer. It's a pointer to a struct data. So the value field is nothing more than a memory address to something that's a struct data. And what is a struct data? It's 2 integers and a pointer. It's a birth, a death, and a legend. So there's an integer birth, there's an integer death, and then there's something called legend, and that's also a pointer. So the legend is the reason this person is famous, and that's not stored here in memory. What's stored here in memory is a pointer to a section of memory with a bunch of strings. So why is this person famous? I don't know, they're rich. And this value field has a pointer that points to a struct data with a birth and a death, and a pointer to another character string. And no reason. So as you're building up your hash table, this is what your memory map looks like. And it's very convoluted. Right? We have a pointer to a table where one entry is a pointer to a structure where one field is a pointer to a set of letters. And if you want to find the legend associated with entry 0, you have to use the pointer to the table, find index 0, get the value field, use that to get to this struct data, get the legend field, take what that's pointing to, that's where your characters are in memory. So all that's going on, and as you're creating this, everything needs to be malloc. Because when you start, before you call a init, no memory has been allocated for anything except the values of variables. So hash is declared to be a struct hash entry star, but it doesn't have a value of any meaning. It's probably equal to 0. So the first thing that you do in ODP 11 was you allocated space for this. It's size of struct hash entry times 101 bytes. You allocate that space, you have hash point to it. And then we set up this part and the 2 integers. So we went through each entry, set in use to 1, deleted to 0. And before we could store that test data, that key value, we needed to set this to point to a block of memory big enough to hold that variable weird. So we took the length of weird, we added 1, did a malloc, had this point to that block, and then did a string copy from weird into that block. And that gets you ODP 11. So that was sample code for ODP 11. So the routine takes a key, which is a car star, and it returns a hash table. So first thing, my hash table is called R malloc. There's a hash size times size of struct hash entry. So this is what R is pointing to. and then go through and make the key point to a block of memory big enough to hold whatever the key is. Use string copy to actually copy the characters from key into key, set in use to 1, delete it to 0. Loop through all hash size entries, and when we're done, we return R, which is the address of this byte right up here in the upper left corner. All right, still with me. So let me talk about ODP 12, and then we want to go back and look at this in GDB. So the reason for what follows is this. Just let me cover that for a moment. Did I have you do that? Or? Yeah, it takes an argument. So what does this main program do? It declares a hash table, pointer to a struct hash entry. It calls a init test, it gives it a string, and it takes what init test returns and it stores that in H. And it exits. Is that a good first test program? Sure. Because if init test is going to seg fault, you'll know that when you run this. But if this program runs without seg faulting, is your testing done? Probably not. All you know is that init test didn't seg fault. But how do you know that it did anything? And how do you know that it did all those things that it was supposed to do? So you really, at this point, want to go in and start looking at H. And start picking out some elements and check the in-use flag, check the deleted flag, check the key. Those are the 3 fields you touched. And if all of that looks good, that's promising, but you're still not done. Because there's lots of ways that you can print out those fields and it looks good, but you don't know if your code actually works. So that's where GDB is going to come in handy. So let me talk about ODP 12 now, and then we'll come back and look at this GDB. So ODP 12, we're writing a new function called save. And the purpose of save, let me move this over. The purpose of save is to write things into our hash table, but it's not the same as the store routine from PA3. It's an easier version of that. It's something you can actually use in PA3 to write your store function. So save takes 5 arguments. It takes the hash table itself, right? That's the array of hash entries. It takes an index, which should be between 0 and hash size -1. It takes a pair of integers, which are birth and death. And then it takes a character pointer, which is a string saying why this person's famous. You do not use your hash function, the thing that takes a string and adds the characters and adds 7 and multiplies and all that stuff. You're not using that in this assignment. You need that for PA3. But for here, we're not hashing the key to figure out where to store it. This routine, you're telling it exactly where to store it in the array. That's what the index is. So if I say save hash, save T to 1900, 1950, person was rich, you should store that data in index position 2. Doesn't matter if it's in use, deleted, you're not asked to touch the in use and deleted flags or anything like that. All we're doing is storing what's called the value field. Okay, this second column. So don't get tripped up by that, right? It's different from PA3 store. So save, give it an index, build a struct data, fill in the birth, fill in the death, allocate space for the legend, copy the legend, and then store this in the value field at the index that you were given. Okay, it's a piece of what you would do in your actual store. Your actual store routine for PA3, you get your key, you hash it, you check here, and you look at the flags to see if that spot's available. If it's not, you've got a collision, so you rehash with a new probe number, and you check that, and eventually you find a place to store it. Say you want to store it in index 17. Now you can call your save function with an index of 17, and it'll actually write those values into there. All right, so the whole goal of ODP 12 is to write this save function. And the algorithm is spelled out here on the bottom. So allocate space for a struct data. That's this block over here. So that's a malloc. And then set table index dot value to point to that. So if your index, well, whatever your index is, table bracket index dot value should be equal to whatever the address of this block is, so whatever malloc gave you back. Copy the birth and death fields directly into here, that's straightforward. And then the legend, remember, is a pointer. So if T is your table, T bracket index dot value equals malloc. Right, that creates the struct data. And then T index dot value, that's a pointer to a struct data. So if we want the birth field, we could say take the thing that points to and pick off the birth field. But we don't usually do that. We use this notation instead. T bracket index dot value arrow birth. So the thing that this points to is a struct data. This is the birth field. So set that equal to the birth, and then do the same thing for the death field. Yes?
If in some situation birth was another structure and wanted to look at the field inside of it, would we just do dot value arrow birth arrow?
If birth was a pointer to a structure, yes, use an arrow after birth.
Okay.
If birth is just a structure itself, then you would say T value arrow birth dot field name.
Okay.
Usually these things will point to other structures, so yeah, it'll just be a string of arrows.
Okay.
So set this equal to your birth, set this equal to your death, and then the legend field is T bracket index dot value arrow legend. The legend field is a car star, right? It's not the letters themselves, it's a pointer to the letters. So your next job is to allocate space where you're going to actually store the letters, and set table index dot value legend field, that's table index dot value arrow legend, set that equal to the space that you're allocating. And then actually copy the characters from the legend argument into this, and that can just be a straight string copy. Right, so this is the challenge of ODP 12. You've got a dot here, you've got an arrow here, you've got brackets here. Those are very different things, right? They're all the same thing, but in some ways they're very different things. And if you're the least bit unsure what the differences are and when to use those, right, that's going to come out in this exercise.
And Monday, right?
Yes. Not so much Monday. I'm not going to hammer this stuff too intensely on the midterm, because this is where I think we are right now in the course. But basic use of arrow and dot, sure, that's fair game. All right, so write some test code, we'll talk about that next. link it together to make a testable image. And I added a little note here, you may or may not need to include a knit test. So I put a copy of a knit test.c /temp. I put a copy of hash.h/temp. If you've got your own init test, you can use that. You can compare it to the one that's there. If you don't have one, you can fix it up, or you can just use the one from /temp. If a init test is in its own file, you obviously need to include that when you GCC. If a init test is included in your main.c, then you don't need to include it, or in your own main.c. So this GCC line, whatever you have to do depending on how you organize your files. Some people will put all the functions in one file, some will break them up. So, user 224. All right. Let's do a 5-minute break, because we're going to go hot and heavy with GDB after this. So let's take 5 minutes to cool our brains. And I'll see you back here at like 5:05.